Yeah, okay, please, Francis, go ahead. Thank you.
Okay, yeah. And sorry I didn't send the lecture notes yet. I'll send them after this.
Oh, sure, yeah, it's okay. Yeah.
Okay, so let's see. Okay, so for today, I want to continue what I was talking about last time. I guess the plan, which hopefully I can get through, is to, I guess I want to start by reviewing what I talked about at the very end, the reformulation of Kähler geometry, which is due to Donaldson. And then I want to talk a little bit about Poisson geometry and Morita equivalences and so on, and then explain how that can be used to reformulate generalized Kähler geometry and how this leads to being able to write down a generalized Kähler potential. So that's hopefully the plan for today. So I want to start with what I talked about at the very end of last lecture, which is Donaldson's reformulation of Kähler geometry. So I'm going to kind of summarize a little bit what I said last time, but feel free to ask for clarification if you don't remember. So here we're starting with a Kähler structure. And the basic idea of Donaldson's reformulation is that we can kind of break this up into two things. The first part is the complex structure plus the Kähler class. And the Kähler class, we can think of it, so it's an H1 of omega 1, because it's a 1-1 form. In fact, you could think of it as H1 of omega 1 closed. So this structure, it depends, it's kind of this topological data along with the complex structure. And the idea is that this class, it defines a holomorphic symplectic manifold. Which I called Z omega. It's a fibration over M, a holomorphic fibration. And it's actually, it's an affine bundle modeled on the cotangent bundle. So if you remember, the basic idea of this is that it's kind of Z, if we restrict to a small enough open set, it's locally, or including, let's include the symplectic form, it's locally just given by the holomorphic cotangent bundle of M with the canonical symplectic form, say U. And the way that it's built up is with affine translation functions. So the affine translation functions, they're affine transition functions, which you can think of as translations. And these are given by Aij, which, if you remember, it was the del operator applied to the difference of two different Kähler potentials. Okay, so this gives an affine bundle. And an important fact, I guess, is that, so what I mean by an affine bundle, it's not a vector bundle, so you can't actually add elements in a fiber like you can on the cotangent bundle, but you can take an element of the cotangent bundle and add it to an element of Z. So you get this kind of addition map. Okay, so that was the first part of the structure. The second part of the Kähler structure.
Francis,
Oh, yeah.
Is there a way of describing globally what is said more explicitly, or?
Yep. I'll give you 2 ways actually in a minute. Oh. 2 other ways that you can think of it. Yeah. So this part is just review from last time. So the second thing is that the metric, so the second part of the Kähler structure is the metric, which is G, or equivalently the actual symplectic form, not just its cohomology class. And this defines so-called brane section L inside of Z. So it's a submanifold of Z, which is smooth, like non-holomorphic. The section property is the fact that the projection map restricted to L is an isomorphism, diffeomorphism. So that's explains the term section, and the brane part. It means that L is Lagrangian for the imaginary part of omega. Okay, so that means that if we take this holomorphic symplectic form on Z and we pull it back to L, well, because L is Lagrangian for the imaginary part, this just becomes the pullback of the real part to L. And this is a real 2 form on L, or equivalently on M, because we have this diffeomorphism here. And so this actually is equal to omega. So in this way, L corresponds to the metric. You can recover the metric by taking the holomorphic symplectic form and pulling it back to L. So this recovers the metric. And if you remember how it was built locally, so if we look at this picture again, let me now upgrade it to include L. So Z omega L restricted to some open set, some small enough open set. It's the cotangent bundle with the canonical symplectic form, and L here was the graph of I del K, where K was a Kähler potential. So what that means is that omega restricted to L, that's the same thing as the canonical symplectic form restricted to minus L del K, or the graph of this thing. And by the property of this symplectic form, that's just D of minus I del K. Or in other words, it's I del bar of K, which is omega. Okay, so let me draw a picture on this page of what's going on. So here is Z omega, here's M, here's the projection. I'm going to shade this in. Maybe also draw the fibers of the map pi. And then we have inside this submanifold, which is L. And here's the key idea, which is that the placement of L inside of Z omega determines a specific metric in its Kähler class. And by the way, you can kind of, from this perspective, you can see why is the metric of a Kähler structure determined by a Kähler potential. From this perspective, well, it's just given by a Lagrangian, and locally a Lagrangian, if we choose a Darboux chart, then locally a Lagrangian is given by a closed one form, which is specified locally by a single function. So I'll come back to this later, but this is kind of the idea to keep in mind. So this is, let me just summarize this as a proposition, which is due to Donaldson, which is that there is a correspondence or a bijection between Kähler structures and holomorphic symplectic affine bundles modeled on the cotangent bundle Z omega plus a symplectic brane section. So in fact, Donaldson calls them not symplectic branes, he calls them LS submanifolds, because they're Lagrangian for the imaginary part and symplectic for the real part. And if we kind of under this correspondence varying omega inside of a fixed class, that's the same thing as deforming L. Okay, and so there's a couple, sorry?
Francis.
Yeah.
To construct Z, you have chosen one particular omega, right? And then what you're claiming is that if I move, and this has one particular L.
Yeah, well, so if you think about it here, what I needed to build Z was just the complex structure and the Kähler class. So the Kähler class,
Okay, the Kähler class.
It's H1 of omega 1. So if you think of omega 1, this is like the sheaf of kind of affine translations or affine symmetries of the cotangent bundle, right? So H1 of omega 1, using like a check description, it corresponds to a space that's locally modeled on the cotangent bundle, but where the transition functions are these translations.
Right, but then when you say that the Ki, Kj are Kähler potentials, is this for which metric?
Right. So when I actually constructed it, starting with the Kähler structure, I did use the details. That's right. I did use the details of this specific Kähler structure to build Z, but just as a holomorphic symplectic affine bundle, it only depends on the Kähler class.
Okay, thanks.
Yeah. So here's a couple more observations. So one, so we have this L inside of the space Z, and so I mean, each fiber of Z is an affine space for a vector space, and in order to give an isomorphism between an affine space and a vector space, you just need a point. So that's sort of what Z is. That's sort of what L is doing. So we actually do get a map, a globally defined map from the tangent from the cotangent bundle to Z. where we send a form alpha, or a covector alpha to alpha plus L. The problem is that this is not a holomorphic. This is only smooth. So this is only a smooth isomorphism. But we can use this to pull everything back and just describe everything on the tangent, on the cotangent bundle of M. So if we do that, it gives us an isomorphism between Z, omega, and L with the cotangent bundle. And instead of the canonical symplectic form, it's the canonical symplectic form plus the pullback with respect to omega, the pullback of the Kähler form omega, and then L, so L corresponds to the zero section. So that's kind of one global construction. So in here, it's kind of maybe a better global picture, but it's more difficult to see that this thing is actually holomorphic symplectic. So what you would need to check is that if you take this form, so this, let me call this omega. So omega, it's going to define a map from T to T star. I mean, it's going to be T of the cotangent bundle. And the claim is that if we define T01 to be the kernel of omega, then this defines a complex structure. So that's something that you would have to check if you were just given this description. But we know it's true because we've given it kind of a purely holomorphic construction as well. Okay, so here's a second construction. Well, first of all, are there any questions about this part?
So the complex structure, you just read from omega as the kernel, right?
Yeah, another way of thinking about it is that a complex structure, now I forget the signs, but you can always write it as B plus, or I guess I omega plus I B, I believe. So, sorry, like this. A holomorphic symplectic form, it will always have this form. So if you take the real part of omega and compose it with the imaginary part inverse, then that gives you a complex structure. So the holomorphic symplectic form, it completely determines the complex structure for which it is holomorphic.
I have a question, actually. When you say that it's not clear to need to show that this is integrable, I think as far as you have a closed form, and you have the right algebraic property, the integrability is a consequence of the closeness. What you just said, if real and imaginary parts are both closed, then this automatically will be integrable. That's what's called Hitchin lemma. This is very well established.
Right. Yeah, I think you're right. Yeah, I'm not claiming that it's particularly difficult, but I just mean it's not like you do have to check something. But yeah, I think you're right.
But so, okay, so you're saying you can use big omega to define a complex structure on Z, right?
Yeah.
And then, so this comes, okay, but I guess it's not, right. You still don't have, there's no sort of like canonically associated metric on Z, I guess.
That's right. Yeah, the metric is really corresponding to L.
Well, I mean, I don't mean like the base metric. I mean a metric on the total space, Z. I mean, does the construction naturally suggest a metric on Z?
I don't think so. I don't think so. Okay, so let me give another construction, which might be useful as well. So let's suppose that mi omega is pre-quantized. So that means that we have this pre-quantum bundle here with the Hermitian metric and the Chern connection, and the curvature of the Chern connection is 2 pi I omega. Then let's define P sub u to be the complement of the zero section, or in other words, it's the associated C star bundle of the holomorphic line bundle. Then we can consider the cotangent bundle of this thing with its canonical symplectic form. And this thing, it has a canonical structure of a Hamiltonian, as a Hamiltonian C star action. So it has, in particular, a moment map, like that. And so we can take the symplectic reduction of this thing. So if we took the symplectic reduction at 0, we would just get back to the cotangent bundle of M. But if we take the reduction at a non-zero point, then we recover the space Z. Okay, so here's another way to see that Z really, it doesn't depend on the particular symplectic form. It only depends, because it only depends on the line bundle, so only on the Chern class. Okay, so that, but we have the metric as well. And so H, this metric, it defines an S1 subbundle, S inside of P. And then we can consider its conormal bundle. And this thing, this conormal bundle, it turns out to be a brane, meaning that it's a Lagrangian for the imaginary part. And so if we reduce this conormal bundle, we recover the brane. Like that. And maybe just one more thing to mention is that, so this being a cotangent bundle, it has a canonical pre-quantization itself, a holomorphic pre-quantization, which is the trivial bundle. And the connection, you just take kind of D and then you add the primitive for the symplectic form. So this gives a holomorphic pre-quantization, and this also reduces. So there's kind of a quantization condition, but it reduces for certain values of the moment map, and so it reduces to give a holomorphic pre-quantization of Z omega. Let me call it LD. So this is a holomorphic line bundle with a holomorphic connection whose curvature is omega. It's omega. But what we can do then is we can take LD and restrict it to L, and this recovers UH nabla. So the pre-quantization of a Kähler structure can also be kind of encoded as a pre-quantization of Z.
Okay. Can you say more explicitly what is mu? I guess you use that you have an exact symplectic form, right?
Yeah. So mu is so on P you have the C star action, and infinitesimally is generated by a vector field, the Euler vector field in each fiber. And a vector field, it defines a function on the cotangent bundle. And that's the moment map. Does that make sense? Okay. There's kind of a really simple example of this construction.
But how do you see this claim that if you take a level which is not 0, then you get this?
Sorry?
Is it? No, I'm just trying to understand why if you get a level which is not 0, you get this Z omega.
There's a couple of different ways. You could do it by kind of a check construction. Another simple way is if you, I mean, it takes some calculation, but you just take omega and you restrict it to this L. So you just choose any connection on U. You can define this conormal bundle, and then you can see what is the restriction of this omega on the conormal bundle, and it'll be like D of H essentially, or like something like D of H. So you can see when you reduce, it will give you something that recovers this the Kähler form. So that's kind of a kind of a straightforward way of doing it. So here's a kind of a simple example. If we take P1 with the Fubini-Studi form, then Z, it should be an affine bundle over P1, and it's just given by the following inside of C3. So it's something like this, and L is the real locus. Okay. So now I want to go back to generalized Kähler geometry. So let me just recall the definition.
Can you go back just 10 seconds to the previous slide? What is, so omega is dx with dy divided by what? 2z or what is?
2z, I think.
Okay. And what is your claim about this LD? I didn't. So what is D?
Sorry?
I didn't understand what is D. What is D? You see, reduces to give a holomorphic.
Oh, here.
Yeah.
So D is a holomorphic connection on L, such that D squared is omega. So it's a holomorphic prequantization.
Oh, okay. Ricci is prequantization. Okay.
Yeah, so it's a little bit weird because I guess if you're on a compact manifold, you wouldn't really expect that. But it's the fact that it's non-compact that it works.
Okay.
So let's recall what is a GK geometry of symplectic type. So this consists of a manifold, two complex structures, a Poisson structure Q and a two-form F. So here we can kind of package everything together the following way. This is a holomorphic Poisson structure. So we have really two holomorphic Poisson structures such that the Poisson tensors share the same imaginary part. And F is a closed two form. And there's a set of equations that are satisfied. One of them is that the difference of the two complex structures is measured by the Poisson structure and the two form. And second, you have this joint 1-1 condition. So F is not really 1, 1 for I plus or I minus. It's kind of split between the two. And this is a possibly degenerate. So this structure is possibly degenerate. But we say that the structure is positive if G is equal to, if this, so this thing here, which is always a symmetric tensor. So if this defines a metric. And in this case, G with I plus and I minus actually defines a generalized Kähler structure. But if you remember last time, it's really useful to not require that the structure is positive in all cases in order to do constructions and so on. It's just useful to include the possibility that it's not positive. And yeah, so basically the goal is that we want to extend Donaldson's picture to this setting. And the new feature here is the presence of the Poisson structure. So the new feature is the Poisson geometry. So in order to kind of proceed, we need to talk a little bit about Poisson geometry and what we can do with them.
Hey, Francis, one thing.
Yeah.
Yes, about the previous construction, this Donaldson construction.
Yeah.
I guess you can interpret this as a canonical deformation of the complex structure in the cotangent bundle each time you have a Kähler class, right?
That's right, yeah.
Okay, so I guess there is some cohomological thing that if you have a 1-1 class, then you can regard it as a 0-1 form with values in tangent of the tangent or something.
Yeah, it's exactly this
tangent of the cotangent. Yeah.
This thing here, right? This is a deformation of the cotangent bundle. So if I put a t in front,
okay,
I would get an entire family, right? When t is 0, it just gives me the cotangent, and when I scale it, it gives me a family, like a 1-parameter family. And that's exactly for the different values. So if we just took, the cotangent bundle and we quotiented it out by C star, we would get kind of like it would be a Poisson structure, but the leaves would be the different deformations. It would give you like in one big family, something starting with the cotangent bundle and deforming it away.
Thanks.
Okay. So yeah, so I need to talk about Poisson geometry and Morita equivalence. Can I ask how much do people know about Poisson geometry? Is it worth going over the definition?
Sure, why not?
Okay, so a Poisson structure on a manifold M, well, one way of thinking about it is it gives you, it's a Lie bracket on the smooth functions. So it's something like this. Right, so it's skew symmetric, satisfies the Jacobi identity, but it satisfies one extra condition, which is a compatibility with the product of functions and the Poisson bracket, which is the Leibniz condition. So it's that f of g times h is f of g times h plus g times bracket of f and h. And a Poisson structure, so you can define it kind of in this algebraic way as a Lie bracket, like this. but it's really encoded by a bivector. So Poisson structure is encoded by a bivector field. We call it Q, which is a global section of wedge 2 Tm, which satisfies an integrability property, which is that the Q bracket Q is equal to 0. So this bracket here is the Schouten bracket. And what it is, it's an extension of the Lie bracket on vector fields. You can extend the Lie bracket on vector fields to multi-vector fields. And the way that it's, so this is equivalent to the Jacobi identity here. And the way that this is related to the bracket is that the bracket of two functions, f and g, it's equal to q of df wedge dg. So let me just say there's a couple of examples. Kind of the 0th example is just setting it to 0. It's a Poisson bracket, but it's the most trivial one. Another special case is if you have a symplectic form. So if you have a symplectic form, it's not a bivector, it's a 2 form. So it's a global section of wedge 2 of T star of M. But omega, it defines in this way, it defines a map from Tm to T star of M. And the fact that, well, I mean, one of the properties of a symplectic form is that this map is an isomorphism, so you can invert it. So you can define Q to be omega inverse, which is a map from T star of M to Tm. And a map like this, which is skew-symmetric, it's encoded by a bivector field. So that's a special example. I mean, it's an important example to keep in mind, actually, that symplectic form gives you a special case of a Poisson structure. It's the case of a Poisson structure where this map is invertible. A second example, which maybe is just nice to keep in mind, is whenever you have a Lie algebra, well, you get an induced Poisson bracket on the dual. So G star has a Poisson bracket. So this was known even to Lie. The idea here is that you think of G inside of the smooth functions on G dual as the linear functions. Then the Lie bracket, or sorry, the Poisson bracket of linear functions is given by the Lie bracket, right? Because the Lie bracket it sends linear functions to linear functions. Okay. So like I said, if you have a Poisson structure, it defines for you a map, which maybe I should call it sharp or something. But I usually just use the same letter. So it's a map from T star of M to T of M. And so it defines, over each point of M, it defines a subspace of the tangent bundle. And in fact, it defines a distribution. So the image of Q inside of Tm is a distribution, but it's actually a singular distribution. So what this means is that a Poisson structure, it leads to a decomposition of the manifold into a bunch of leaves. But the fact that it's a singular distribution, it means that the leaves, they're not necessarily of the same dimension. Okay, but in any case, you get this distribution, so you get this decomposition into leaves. And given each leaf, so given a leaf, L inside of M in this distribution, then Q, it induces a symplectic structure on the leaf. So that's why the leaves are called symplectic leaves usually. Kind of a nice example of this is that for the symplectic leaves of the dual of a Lie algebra, they're the coadjoint orbits. So the kind of the upshot of this, though, is that we can kind of think of a Poisson structure Q as a decomposition of M into symplectic submanifolds. So it's some kind of really complicated singular structure of all these different leaves fitting together, and there's this kind of symplectic form that's varying in a kind of a nice way on the leaves. Okay, so is everyone okay so far? Okay, so yeah, so I want to introduce this idea, which is due to, it actually goes back to Lie, but then it was kind of brought back by Weinstein, which is the idea of a symplectic realization. And the idea here is that we replace the singular decomposition of a Poisson manifold into symplectic leaves by a map. And so all of the kind of the singular structure of the leaves, it gets kind of encoded instead in the kind of the singularities of a map. On the singularities, yeah. So this is the notion of a symplectic realization. So what the idea is that a symplectic realization of a Poisson manifold MQ is a symplectic manifold, say S omega, together with a surjective submersion pi from S to M, such that if we push forward, so we take the symplectic form on S, we invert it to get a Poisson structure, and then we can try to push it forward, and the condition is that it pushes forward to Q. So if you think about what's going on here, you have on M, you have the Poisson structure, so it has all this kind of complicated symplectic leaf structure, but you're replacing it with S, which is a symplectic manifold. So there's just the single submanifold is the symplectic leaf, but then you're relating the symplectic manifold to M with a submersion. So all of the kind of the singular structure, it's all encoded in the map pi. So let me just list, so there's, I mean, if you're just interested in learning about Poisson geometry, there's a paper of Weinstein, which is called The Local Structure of Poisson Manifolds. It's from the 80s, but it's a really great paper. But this idea of symplectic realization, it actually goes back to a paper of Lee. And I think he was using these ideas even when he was trying to integrate Lie algebras. Okay, but let's look at the picture of a symplectic realization. So I'm going to draw a picture of what's going on. So here's my S omega, here's my M Q, and here's my submersion. And it has these fibers. So there's a kind of a few observations that we can make about this. So the first thing is that we can take the kernel of the projection map, and that gives us a foliation, an integrable distribution of the symplectic manifold. So the leaves are these fibers here. But what we can do is we can use the symplectic form to define an orthogonal. So let's take D to be the orthogonal complement using the symplectic form. I don't know how to write it, like this maybe. So it's all the vectors in the tangent bundle of S that pair using the symplectic form to 0 with the tangent to the fibers of pi. So that gives us these kind of other distribution. And well, here's something you can do. So let me take a function on M. Then I can pull it back to get a function on S. Now, if I have a vector in the kernel of pi, well, if I apply it to the pullback of F, I get 0. Okay, but using the symplectic form, I can rewrite this in the following way. I can rewrite it as omega, the symplectic form, of the Hamiltonian vector field of the pullback of F paired with V. So what this is saying is that D is generated by the Hamiltonian vector fields of the functions on M. Does that make sense? And so, like, because of this map pi, we get kind of an embedding like this: smooth functions on M into smooth functions on S, such that it respects the Poisson bracket, right? You have the Poisson bracket coming from Q, you have the Poisson bracket coming from omega, and the pullback map, it respects these. So what this is telling you is that this C in these functions on M, it gives you a Poisson subalgebra on S. And what that means is that if you take the Hamiltonian vector fields corresponding to functions on M, they're closed under the Lie bracket, right? So what this tells us is that D is involutive. So D is an integrable distribution. So there's actually some kind of tangent submanifolds like this. So what this means is that it actually determines another space. And kind of following a similar argument, you can show that the Poisson structure omega inverse, it descends to give a Poisson structure on the quotient of S by this foliation. So here you have S, kind of the least space of the second foliation, and it gets a Poisson structure Q prime. So let me kind of draw another picture. Here's S omega. Here's my original Poisson structure MQ. Here's my symplectic realization. It has these fibers. And what we've seen is that the orthogonal distribution is also involutive. And so kind of ignoring issues that the leaf space might not be whatever, Hausdorff. I mean, if we want, we can just work locally. What we see is that we get actually out of this a second Poisson manifold. So the upshot is that symplectic realizations, they naturally come in pairs. Here's an example that you've probably seen. We have, if we have M omega, a Hamiltonian G space, well, we can take the moment map. And this is actually a symplectic realization. And so we get kind of this dual polarization, and if you work out what it is, it just gives you the quotient space like that. So that's an example of this phenomenon. So the kind of the upshot of this is that this kind of discussion, this leads to a kind of a new equivalence relation for Poisson manifolds that is weaker than isomorphism. These Poisson manifolds, they're not necessarily isomorphic, but they are equivalent in some way. So this is the notion of Morita equivalence.
Do you mean the symplectic quotient or MG, M quotient?
Not the symplectic quotient, literally MG, because this is a Poisson manifold.
Okay, thanks.
Yeah. So this leads to an equivalence relation for Poisson manifolds. And it's weaker than isomorphism. So this is the notion of Morita equivalence. And it's due to Weinstein and Zhu, but really the definition, it goes back to Lee, actually. He considered this. So a Morita equivalence between Poisson manifolds M1 Q1 and M2 Q2 is a symplectic manifold S omega together with surjective submersions pi1 from S to M1, pi2 from S to M2, such that, well, number one, this map pi1 or 2, it pushes forward the inverse of the symplectic form to either Q1 or Q2, but actually there's kind of a little sign issue. We have either, so one of them pushes to positive the Poisson structure, the other one pushes to minus the Poisson structure. Anyways, that's not a big deal. Second property is that the kernels of pi1, well, of the derivative of pi1 and the derivative of pi2, these are symplectic orthogonal. And finally, this is kind of a technical condition which you can ignore, is that these maps are complete. It's a notion of completeness for symplectic realizations, which means that if you have a function on the Poisson manifold whose Hamiltonian flow is complete, then if you pull it back and take the Hamiltonian flow of that thing upstairs, that will also be complete. But yeah, it's kind of a technical condition, which is not really important. So here's the picture again. And so maybe I'll say a few words about how to think about what's going on. So one thing you can notice is that we get these Poisson algebras embedded as subalgebras of the Poisson algebra of the symplectic manifold. And this whole business about the symplectic duality of the fibers, or sorry, symplectic orthogonality of the fibers, what this says is that if you take the Poisson bracket of something coming from the first manifold with the Poisson bracket of something coming from the second manifold, it gives you 0. And in fact, the functions on M1 is actually precisely the functions that commute with the functions on M2. So this is what Lee called a polar dual. And this is actually really, this is kind of useful for understanding what's going on here. Because we can take the intersection of these, of the functions on M1 and the functions on M2. So that kind of embeds like this. And so what are these functions? These are exactly the functions that commute with everything, right? These, because they live in CM1, they commute with everything in CM2. And because they live in CM2, they commute with everything in CM1. So these are the Casimirs of either Q1 or Q2. So the Casimir functions on a symplectic manifold are the functions that, if you bracket them with anything, they give you 0. And the way that you should think about them is that these give you the functions on the space of symplectic leaves.
So the intersection is taking place in C infinity S.
Yeah, exactly. Yeah, so I'm just saying that like inside of C infinity of M1, you have all of the functions that Poisson commute with everything in C infinity of M1. In C infinity of M2, you have all the functions that Poisson commute with everything in C infinity of M2. But they actually are isomorphic because they both embed inside of C infinity of S as the intersection of C infinity of M1 and C infinity of M2. So what that means, does that make sense?
Yeah, I think so.
And so if you think about Casimir functions as the functions on the space of symplectic leaves, what this is telling you is that M1 and M2, they kind of have the same space of symplectic leaves. And you can actually, you can define the correspondence kind of explicitly. Say you take a symplectic leaf over here. Let me draw it here, kind of L2. I can take a point, Q. I look at the fiber above it. And I project this fiber. So I take, here's pi 2, here's pi 1. So I take kind of pi 2 inverse of Q, and then I project it down with pi 1, and that will give me a symplectic leaf down here, L1. So the Morita equivalence, it actually gives you a way of kind of mapping, of giving a correspondence between the symplectic leaves of the two Poisson structures. Let me just say one more thing, which Weinstein proves in that paper. He shows that the Poisson structures, so let me draw a picture like this. Again. So if you take a point here, Z, which goes to P, and it goes to Q. So what Weinstein shows is that the Poisson structures kind of transverse to P and to Q are isomorphic. So the kind of the picture kind of globally is that the Morita equivalent Poisson manifolds have the same global space of symplectic leaves, and kind of locally, it looks like the difference between them is that you've kind of added a symplectic direction. Okay, so there's so here's kind of another important fact, which is that in many cases, a Poisson manifold, it admits a canonical Morita self equivalence. So it's something like this, which goes from the Poisson manifold to itself. And this thing is the symplectic groupoid. Of the Poisson manifold. And in particular, it has the structure of a Lie groupoid. So maybe kind of an important thing to keep in mind is that if you have Morita equivalences between Poisson manifolds, you can actually compose them. So you can almost think of them as kind of morphisms between the different Poisson manifolds. And this symplectic groupoid, it acts as the identity. If you compose it with anything, it acts as the identity. So I'll give a couple of examples of this. So let's just go through our list of Poisson manifolds. If we take the zero Poisson structure, then the symplectic groupoid is the cotangent bundle. And you can get a bunch of non-trivial Morita self-equivalences given a closed two form. Then you can take the cotangent bundle and take the symplectic form and add to it the pullback of B. This gives a Morita equivalence. If you start with a symplectic manifold, then the symplectic groupoid, well, you can take it to be the product of M with itself, but you put the symplectic form plus omega on the first factor and minus omega on the second factor, and the two maps to M are the two projection maps. And if you have any two symplectic manifolds are Morita equivalent, in a similar way. So actually, I mean, this is not completely correct in the sense that people usually care about having the same fundamental groups. Usually you want the fibers of a Morita equivalence to be simply connected. So that would kind of introduce some complications here, but I think it's not important. If you have the dual of a Lie algebra, then the symplectic groupoid is given by the cotangent bundle.
Sorry, Francis.
Yeah.
I'm a bit confused. So how does this fact that any two symplectic manifolds are Morita equivalent fits with your comment before that you said if you have two Poisson manifolds which are Morita equivalents, then the space of functions in the the functions in the space of symplectic leaves get identified.
Yeah. So in this case, there's only a single symplectic leaf. So the Casimir functions are trivial. They're just constant.
Oh, okay.
Yeah.
Thanks.
Yeah. So the symplectic groupoid of the dual of a Lie algebra is given by the cotangent bundle of any integrating Lie group. So here it's a group such that the Lie algebra is G. But it's so if we look for the zero Poisson structure, we also got a cotangent bundle. Here I didn't tell you the two maps to M are just the projection. But for the cotangent bundle of a group here, you have two maps to G dual. And one of them is the left trivialization, and one of them is the right trivialization. So there's an important construction which is due to Burston and Radko. which is about how can you construct examples of Morita equivalences. And this idea is so just to say where I'm going. So I don't know, if you look at this example here, it looks very similar to what we were just talking about in Donaldson's reformulation of a Kähler structure. So we want to go kind of in the direction of constructing Morita equivalences associated to generalized Kähler structures. And the method of construction, it's the kind of the prototypical example is due to Burson and Radko. And their construction goes in the following way. So I just want to describe this construction, and then I'm going to give the result for generalized Kähler structures. So if you have a Poisson manifold, and you have a closed 2 form, then you can try to define a new Poisson structure. And so there's a kind of a formula for this, which is QB, which as a map from T star to T is defined with the following formula. And so this is a new Poisson structure, which is called the B field transform of Q. And I think this is due to Chavera. Okay, so this construction might not work if B is too big. So there's a condition, which is that identity plus B composed with Q from the cotangent bundle to itself. This has to be invertible. So if you have this, then you can define this new Poisson structure, which is called the B field transform. And so the construction due to Burson and Radko, they show that actually Q and QB are Morita equivalent. And here's how it goes. So you let sigma omega be the symplectic groupoid of MQ, then you take sigma omega, so it has these 2 maps to MQ. But what you do is you pull back B using this map T, and you add it to omega. But now when you do this, so this map here remains kind of a Poisson map, but this map here, you need to modify the target. It goes to QB. So this gives a Morita equivalence. So yeah, so let me just say this B field transform, the way I wrote it down, it's a little bit hard to understand, but one way of thinking about it is that QB, it has the same symplectic leaves as Q, but we add the pullback of B to each symplectic leaf. So remember, a Poisson structure, it induces a decomposition of your manifold into leaves that have Poisson structures. If you have a global closed 2-form B on the manifold, you can pull it back to each leaf, and that changes the symplectic structure. And if B is small enough, it will remain invertible. So that's how you can change the Poisson structure. And I mean, basically, since you're not changing the symplectic leaves at all, you're going to get something that's Morita equivalent. And this is what this is the construction of Burston and Radko.
Is this the same as regarding Q as a Dirac structure and tangent plus cotangent and doing B field transformation?
Yeah, exactly.
Okay.
Yeah. Okay, so far everything that I said, it was.
I'm sorry, can you repeat what your question was, Mario?
Yeah, that you can think of this as a B field, of the B field transformation of the Dirac structure defined by Q. So you take the graph of Q inside tangent plus cotangent.
Yeah.
And do a B field transformation. B is closed, so it's an automorphism.
Okay, yeah.
Of the equivalent. So this gives you another Dirac structure. And if B is small, then the new Dirac structure is also Poisson.
Okay, yeah, thanks.
Yeah, so so everything that I said so far, it was in the smooth category, but it's still true in the holomorphic category. And in particular, this Burston and Radko construction, it still actually works in the holomorphic category. So you can do B-field transforms of holomorphic Poisson structures. That will give you a new holomorphic Poisson structure, and those things will also be Morita equivalent, and it's the same construction that works. Okay, so let me now go back to generalized scalar structures. So I'm kind of mindful of the time. It's been over an hour, so I'm just gonna say this part, and then we can decide what to do from there. So this will be kind of quick. So recall a generalized scalar structure, the way that we're thinking about it is with two holomorphic Poisson structures and a two-form F. And so here you can see maybe the relevance of Morita equivalence, because sigma plus and sigma minus, they are not isomorphic. But they are closely related. In particular, they have the same imaginary part. And so in particular, they have the same symplectic leaves. So the kind of the natural question is, are they Morita equivalent? So in fact, this goes back to Marco's original paper about branes on Poisson varieties. I mean, it's actually implicit in the definition of the setup, which is that sigma plus and sigma minus are related by, or are B field equivalent via F. In other words, if we take, so sigma plus is actually equal to the B field transformation of sigma minus with F. If we go back to the defining equations, these ones here, these are actually the equations that tell you that sigma plus and sigma minus are related by a B field transformation given by F. So that's exactly what this equation is saying. Okay, so because of this, you can basically run the Burston Radko construction and get a Morita equivalent. So this was done in a paper of Marco and Mike Bailey, which says that the holomorphic Poisson structures, sigma plus and minus, these are Morita equivalent. And the construction is the Burstyn-Radko construction. So we start with, I mean, it has to be modified to work with holomorphic Poisson structures, but it's essentially the same logic. So you let sigma omega minus be the symplectic groupoid of I sigma minus. So it goes like this. And then we define Z omega to be sigma omega minus plus the pullback of F. And so note, this is again something that you have to prove, is that this omega defines a new complex structure for which it is holomorphic symplectic. Once we do this deformation, the map S, it still gives you a holomorphic Poisson map like this to I minus sigma minus. But now T, it's no longer going to be holomorphic or Poisson. It's going to be actually holomorphic Poisson when we think of it as a map going to I plus sigma plus. This is now holomorphic Poisson. Okay, and so this is how we get the Morita equivalence. And the claim is that this holomorphic symplectic manifold, it is the holomorphic geometry underlying a generalized scalar structure of symplectic type. And this is analogous to the complex structure plus Kähler class.
Sorry, Francis, could you go to the previous page?
Yeah.
And sorry, okay, so I see. Yeah, okay, because yeah, sigma minus is invertible in this setting, so it has a symplectic groupoid, I guess.
Sorry.
In this setting, is sigma minus like invertible?
No. So there is this question about existence of symplectic groupoids, which I didn't address.
Oh.
So you have, I mean, it's definitely not obvious that every Poisson structure has a symplectic groupoid, and it's actually not true. There are some obstructions, but they're not. I mean, in many cases, they exist. The symplectic groupoid exists, and even if it doesn't exist, you can still get kind of a local groupoid.
Okay.
So if I forget about fundamental group and everything's simply connected, then groupoids do exist always, right?
Say it again.
If I assume that everything is simply connected, do groupoids exist? Or...
So it has to do about the geometry or the topology of the symplectic leaves. So for example, even if the Poisson manifold was simply connected, the leaves might not be.
Right. Okay.
And it has to do with something with the second homotopy groups of the symplectic leaves.
Okay.
If things kind of vary too wildly, then it will obstruct. the existence. So the
Can you say what is sigma as a smooth manifold?
sigma?
Yeah.
Not in general, no.
And only you said only T is holomorphic. S is not.
S is holomorphic. So S. So initially we had S and T going from this space to M with I minus and sigma minus, and S and T were both holomorphic.
Oh, okay.
Then we modify by adding on the pullback of F, so we get this Z omega. So now S, it's still holomorphic, Poisson, as a map to I minus sigma minus. But T is no longer holomorphic Poisson as a map to I minus sigma minus. It's now holomorphic as a map to I plus sigma plus.
Oh, I see. Oh, okay, I see. Yeah.
So you can kind of think, because we modified this form here by adding the pullback of F, it's messed up the target. It's messed up this T. So we have to change the domain of T. If we added on instead S star of F, T would be fine, but we've kind of messed up S here. We'd have to change the domain of S.
Okay, yeah.
That's kind of the way that it works. Yeah, and describing the symplectic groupoid in general, it can be quite, well, I mean, so usually you want to take it so that the fibers of S and T are simply connected, which means that you kind of have to consider the universal cover of the symplectic leaves, for example. So it could be kind of wild. But I'll have some examples where it's kind of well behaved.
And also, yeah, maybe just for the record, I mean, if you're more than welcome to speak next week as well.
Yeah, okay, because I think that might be necessary. Yeah, I'm sorry that it's going over.
No, I mean, a lot of questions. I think it's good.
So I just wanted to end on maybe with the kind of the main theorem. Yeah, so let me end with the main theorem of the paper, Morita equivalence in the generalized scalar potential, which is about the reformulation of generalized scalar geometry of symplectic type. And then next week, I'll talk about the applications to the potential.
Okay, yeah, great.
So, so here we've described this space Z. Let me draw a picture of it, which is going between the two Hitch and Poisson structures. By the way, there's kind of a simple corollary of this, which is that sigma plus and sigma minus are locally isomorphic. So I mean, they're globally not the same, but around every point I can find a little open set, and I can find an isomorphism between sigma plus and sigma minus. And the proof is really simple. You choose, so say you have a point here, sigma in sigma plus, you have the corresponding point in sigma minus, and you just take a point that maps to each. Then what you do is you choose a little Lagrangian submanifold. It's a holomorphic Lagrangian such that pi plus restricted to this lambda and pi minus restricted to lambda isomorphisms or local isomorphisms to some open sets. If you do that, then you can invert one of them. You can kind of go backwards and then down, and that will be an isomorphism between the Poisson structures. Okay, that was just a little aside. Okay, but yeah, so basically the claim that I've made though is that this holomorphic symplectic manifold, it encodes the underlying complex geometry of a generalized scalar structure. So the question is, where is the smooth data encoding the metric? And so to answer this question, we need to kind of recall a fact, which I haven't actually told you. But remember, we built Z omega by taking a symplectic groupoid. So this sigma omega that we used in the construction, this is a symplectic groupoid. So we didn't start off with an arbitrary Morita equivalence when we did the construction. We started off with a symplectic groupoid, and then we deformed the complex structure on it and the symplectic form. But this thing being a symplectic groupoid, in particular, it is a groupoid. So I guess you can think that it's actually defining like a category, like the points of sigma are a category, are the arrows in a category, and the objects of the category are the points of M. So what this means is that we have an embedding from M to sigma, which sends each element to its identity arrow. So you get this natural embedding of M into the groupoid. Let me just bring this to the next page. So it has the property as the following properties. The first one is that it's a section of T and S. So in other words, it's a bisection. So it's a section of both of the two maps. That's why it's called a bisection. And the second fact is that it's actually a holomorphic Lagrangian, i.e., it's a holomorphic Lagrangian. So if we now consider inside of Z omega, which remember is the same space, but with a deformed symplectic form, we get a submanifold, which I'm going to call L now, but it's really the same thing as the image of epsilon. And this is a non-holomorphic bisection. So, originally it was a holomorphic Lagrangian, but we deformed the symplectic structure and the complex structure, so it's no longer a holomorphic or Lagrangian, but it's still sitting inside, and it's a section of the two maps. Okay, but we can also consider what happens when we take omega and we restrict it to L. We pull it back to L. What we get in this case, if you remember how omega was constructed, it was omega minus plus the pullback under T of F. So that's the same thing as this thing restricted to epsilon. So now we can use some of these facts. This fact here means that this vanishes. And then this fact here, it means that we just get, in the end, F. So you can recover F, and therefore the rest of the structure, from L. So that's the upshot, is that L encodes F, i.e. the metric. So this is the main theorem. Which is that a GK structure of symplectic type is equivalent to a holomorphic symplectic Morita equivalence along with a brane bisection L. Okay, so I guess I'll end here. So it kind of achieves the generalization of Donaldson's picture to the setting. And so next time, I guess, I'll talk about some of the applications to generalized scalar potential. I could talk about also construction of examples, and also it has kind of application to understanding this kind of flow deformation, which I talked about last time. Okay, so yeah, I'll end it here. And yeah, sorry about taking.
Yeah, thanks, Francis. Yeah, no problem. Any more questions? Okay, so yeah, well, we look forward to it next week. Yeah, thanks, Francis. Thanks, everyone.